Throughout history, humanity has wrestled with the concepts of absolute space and time. Surprisingly, it appears that the idea of an absolute position is little more than a human invention. In essence, the universe is a colossal, ever-expanding expanse populated by celestial bodies. Imagine, if you will, all the stars, planets, black holes, and cosmic dust suddenly vanishing. What would remain is a boundless, uncharted realm of empty space. Yet this infinite void still harbors countless secrets. Consider our ancestors, such as the ancient Greeks. Aristotle and other brilliant thinkers of his era believed that Earth sat at the center of the universe. Why? Because it felt as though we weren't moving. This notion is deeply insightful from a modern physics standpoint. Even though we're traveling around the sun at about 18 miles per second, and the entire solar system orbits the Milky Way, we do not feel any of it. The Greeks found it perfectly logical to assume that Earth was at the universe's center, since all objects seem to fall toward it. Only with Einstein's groundbreaking ideas did we begin to understand why we cannot sense our motion through space. Einstein showed that it's impossible to determine whether we are truly moving or at rest. As Stephen Hawking described in A Brief History of Time, this realization obliterates the concept of absolute space. Envision space as Newton did, a vast container in which events unfold. Drop a ball, catch it a second later, and from your perspective, it seems to return to the same spot. Yet in that single second, Earth has traveled about 80 miles around the sun. From another vantage point, the ball moved along a completely different path. The answer depends solely on the observer's frame of reference. Einstein thus concluded that absolute space does not exist, an elegant but challenging concept to fully grasp. To appreciate how astonishing our changing position in space truly is, consider the time of the dinosaurs. According to NASA research scientist Jesse Christensen, the stars we see overhead today were not even present when those ancient creatures roamed the Earth. Our solar system takes roughly 200 to 250 million years to orbit the galaxy's center, and the last time we were in this particular region of the Milky Way, the very first dinosaurs were just emerging. For perspective, the Stegosaurus thrived between 156 and 144 million years ago, whereas the Tyrannosaurus rex lived between 67 and 65 million years ago. Intriguingly, the T-Rex existed closer in time to humans than it did to Stegosaurus. Over these millions of years, as dinosaurs lived and died, our solar system traversed entirely different sectors of the galaxy. As we continue our cosmic voyage, who can say what life might inhabit Earth the next time we circle back around? Our ever-shifting position in space is tightly bound to the principle of relativity. Put simply, relativity holds that measurements of space and time depend on the observer's motion. There is no absolute frame of reference. Space and time are influenced by where we stand and how we move. Einstein elevated this idea to a core principle. If you're not accelerating, just moving at a constant speed, no experiment, no pendulum, no atomic decay measurement, no electromagnetic test can reveal whether you are moving or stationary. Since absolute motion cannot be measured, the notion is meaningless. This insight led to Einstein's theory of relativity, which underpins our current understanding of the universe. Newton's laws tell us that two observers moving at constant velocities relative to each other will witness the same physical phenomena. In other words, there is no such thing as an absolute state of rest. When electromagnetism emerged in the 19th century, it appeared to offer a way to detect absolute motion, but experiments failed to confirm this. In 1905, Einstein showed that no experiment could reveal absolute motion. Instead, Newton's laws needed refining, though these corrections only matter when approaching the speed of light. Experiments in particle accelerators verify Einstein's predictions. As particles approach light speed, their mass effectively increases, making it ever harder to push them any faster. No material object can surpass this cosmic speed limit. Visualize the observable universe as a sphere stretching about 46.5 billion light-years in every direction from our vantage point. Gazing deeper into space means looking further back in time, and distant light becomes more and more redshifted. This leads us to ponder the universe's shape. We know it is expanding, and we observe the same ancient radiation, remnants of the Big Bang, no matter where we look. According to the theory of inflation, the universe is likely far larger than the portion we can see. When we measure its curvature, it appears flat, as if there is just the right amount of matter and energy to balance it perfectly. This precise flatness suggests that our observable region is only a tiny fragment of a vastly larger whole. Both Newton and Einstein agreed that time flows forward, but no physical evidence suggests it can run in reverse. Why does time move in one direction? One explanation lies in the second law of thermodynamics, which states that entropy, or disorder, constantly increases. Over billions of years, the universe has evolved from a state of lower entropy to one of immense complexity, reinforcing a forward arrow of time. Another idea is tied to cosmic expansion. As the universe expands, it pulls time forward with it. If the universe ever reached a maximum size and began to contract, would time reverse? Such speculation leads to paradoxes, showing just how much we still have to learn. By examining the faintest and oldest light in the cosmos, the cosmic microwave background, we use it as a sort of cosmic ruler. The further we look, the earlier the universe we see, and this data helps us determine how space is curved or stretched. With these measurements, we confirm that space is strikingly flat. Ultimately, by studying the earliest epochs of the universe and interpreting the subtle ripples in primordial light, we gain profound insights into the nature of space, time, and our place within this grand cosmic tapestry.